And with that, um, we'll go ahead and jump into our final talk with Ali Koretzky. Uh, Ali is the head of AI and machine learning and audio science innovation at Splice. And he's here to talk about the current landscape of AI and audio. How's it going, Ali?
Hi, Joshua. Going well. Thanks for having me.
Yes,
Hi,
thank you very
everyone out
much.
there.
Great. I will go
All
ahead and turn
right.
over the mic to you. Thank you very much. And
Sounds great. And I'm going to start sharing my screen. All right. Screen-wise, all good?
all good.
All right. Okay. Hi, everyone. My name is Alejandro Ale Koretzky. I'm the head of AI and audio science at Splice. In the next 45 minutes, I might run a little long actually, but hopefully 45 minutes only. I'm going to do a little bit of a blend of the journey, my journey, and some of the work that me and my team have been doing for the past few years. Before Splice, at Splice, and then some intuitions in general around machine learning and specifically applied to audio and in the context of music. How do we keep humans at the center? So it's going to be a blend of a little bit of everything with some cool demos. So hopefully you will all enjoy this. So a little bit about me. I already said I'm head of AI at Splice. My background is in electrical engineering and telecommunications engineering. And for the past almost 20 years, I've been working at times at the union, at times at the intersection of applied research, audio DSP, machine learning, also image processing, but also product management and UX. I used to be a designer a million years ago, so I care a lot about product experience. I've also been an entrepreneur myself as a founder, advisor, mentor, currently mentoring teams at Techstars, and also a connection with music. That's something very, very special for me. And given that I'm giving this talk from my home country of Argentina, as cliche as it sounds, I love football stakes in Argentina as well now, especially that we won the World Cup. So that's pretty much me. And I usually start this with a very holistic view of machine learning in general for those that are still trying to grasp what this is all about. And I like to define it as a new paradigm of automation. If we think about, and I like to use this kind of like an analogy with the box. And when we think about what the revolution of software has been for the past, almost 100 years, and we can describe it as a revolution on automation. And what we have been doing for a long time is using our domain and our understanding about the structure, the attributes, and what we can call the distribution of our input data. And based on what we want to happen at the output of the system, we derive and implement a series of operations or rules to try to automate certain process, and in a way automate decision making. That's pretty much how, very holistically, we can define what the great era of software gave us, and an incredible era of automation. And these rules of operations, at the end of the day, what they do is they describe a model, right? And in this case, I'm using like a clear box because this model has been built based on our knowledge and understanding, so we have full visibility and control over what's happening inside this box, right? And what has been happening, it's already been a few decades, but especially the past 10 years with the third wave of AI brought by modern machine learning, is that this box has become more and more opaque. And this is because of the advances on modern AI, specifically machine learning, and more specifically the role of artificial neural networks of considerable size and complexity, also known as deep learning. And we know that this in turn has been unlocked in some way by availability of data at scale and computational power. And at the end of the day, one way to describe it, the way I like to describe it, is that this new era is a new paradigm of automation where we start automating the automation. And that has several implications. On the one hand, some mind-blowing capabilities that were unimaginable up until only a few years ago, but at the same time, everything has a price. So when going from a deterministic approach to a probabilistic approach to problem solving, a few things need to be taken into consideration, especially when we're building products and experiences that leverage AI technology. And many of you out there might have done some machine learning without even knowing it, but in its most basic expression, if you ever fit linear regression to some data set, technically speaking, you've used machine learning in possibly in its most basic form. And for me, the beginning of the journey in data science in general and predictive systems, it started almost 15 years ago, where I started working on traffic prediction systems from some credit card companies, doing time series analysis and a whole bunch of stuff that today we call data science. And that piece of work is available online somewhere for those interested. So when it comes to solving problems, whether it's in audio or any domain, the dilemma of should we go for a clear box approach or a black box approach? And the answer is there's no right answer. It really depends on the type of problem. It really depends on the constraints of the under which we're operating, based on the kind of value that we're trying to unlock, based on the kind of product that we're trying to build. So it really depends. And I like to show this apparently simple example. This is like a homework during my master's from 10 years ago. Like, we were forced to basically solve OCR, optical character recognition, with a clear box approach. And very soon, something that's, may seem like it's relatively simple becomes extremely complex when you try to solve it with the rules. There's a ton of different steps, and each of them, has its own shortcomings. And when you start chaining pipelining the different processes together, you end up with something extremely complex. And this is, what you can also call old school feature engineering. So it can be a lot of fun, but also a really bad way to solve certain types of problems. And in this case, you end up building your own decision tree based on the rules and your understanding of the system, as I was mentioning at the beginning. And no matter how much time we spend on something like this, the system will not be robust, especially because it's a noisy problem. Think about handwritten digits. So having a system that can really bring robustness and predictability is extremely hard with that approach. So there's lots of problems and lots of data domains that are inherently noisy, that you could describe them as noisy, and audio and music are not the exception when we're trying to build AI systems. So imagine going from just simple OCR, and now suddenly someone tells you, I want you to take this picture and write a program using a clear box approach that identifies all the text, extracts what the text is saying independently of perspective, lighting, occlusion, and so on. So if you ever come across a problem statement like this, I suggest you just quit, because it's gonna get ugly very soon. So for these type of problems where maybe a more black box approach is more appropriate, at a very high level, and I'm making an oversimplification of what's happening, going back to this idea of linear regression, and imagine that now you have thousands or hundreds of thousands or millions of hundreds of millions of these equations where The coefficients are learned automatically from data instead of being derived based on our own human observations of the system. And a lot of this stuff is not new. Convolutional neural networks have been there, almost 40 years now. So a lot of this stuff is not new, but in terms of the conversions of applications, data, computational power, the past 10 years have been really revolutionary in terms of the complexity of problems that we've been able to solve that only a few years ago would have seemed impossible. So this phrase, I don't know, one can have different opinions, but in a way AI is really a new paradigm of software and a really, really powerful one. And with that short intro and talking about impossible problems, my journey at the intersection of audio, music, and ML started like 10 years ago. While I was doing my master's at USC, one day I had this sort of realization, which is obvious but not obvious at the same time. And for anyone out there who enjoys music, either listening or creating music, it's a very historically asymmetrical thing. There's some people that create the music, they mix it, they deliver it in this sort of a black box, stereo format. And then for the passive listener to enjoy what was put together on the left side. So one day, sort of random, but I had been thinking about this, I asked myself, is there any way that I can go backwards? What if I took a mix and try to recover the underlying components, which is a problem known as audio source separation. And it became kind of like my research topic during my master's, and I almost became obsessed with this problem. And there's a nice history after the fact. A spin-off that I built was called TuneSplit, and this is kind of like at the end of the journey. The technology that me and my team developed now almost 8 years ago did. It could take any song and extract the vocal. It goes on and on. Is the audio coming out okay? Yes?
Yep, all good.
All right. So this is a very complex problem. So I'm going to illustrate a little journey. So where do we begin with a problem of that kind of complexity? So what if we gave it a shot at solving this with a clear box approach, which is the way I started. And so if we want to understand the domain and what's happening, I can start analyzing, the waveform representation of audio. And I can start, analyzing maybe the envelope, try to see what's going on. And kind of like the question becomes, if I'm trying to isolate vocal content, where are the vocals in this mix? And obviously with this representation in the context of a mix, it can be quite challenging or even impossible. I can zoom in, I can try to find the vocals there, but likely I'm gonna fail miserably. So starting with this idea of understanding the domain, this domain knowledge is what allows me to start, with a clear box approach and really keep pushing and see how far I can get. And one of the things that we do in signal processing in general is to use mathematical and statistical techniques to analyze, transform, synthesize the information with certain objectives. And in this case, we know from that domain that there's more than one way to represent this audio signal. And while a plain waveform is not that interesting for this specific problem, we know that maybe using the Fourier transform, I can expose certain patterns that were not as obvious in the original representation. So in this case, I have the magnitude short time Fourier transform of Set Fire to the Rain by Adele. And once again, based on my domain knowledge about speech processing and all that, I can start figuring out, okay, maybe I can derive a set of rules because I know that human voice features a fundamental frequency that describes the frequency of vibration of our vocal cords. I have a different type of sounds, fricatives, that are not produced by vibration of our vocal cords, and I know that there's a number of harmonics on top of that fundamental frequency, the formants of speech that give each of us the quality of our voice. So what if I try to build a system where, okay, maybe I can start identifying vocal sections from sections that don't have vocals? This is a very old problem called vocal activity detection with background in communication. Maybe with that, I can build a small classifier with some heuristics that allows me to differentiate between the two types of voice. And maybe, I can also detect the fundamental frequency. There's many techniques out there that exist. And maybe with that, I can apply some sort of harmonic mask and somehow extract, by applying that mask, extract the vocals from the mix. And that was the first approach that we followed. And this is kind of like the output of that approach. So more or less, but not really there, right? And we're talking about a single vocal there. So going back to these problems that become exponentially more complicated the moment you start, not adding complexity, but dealing with the real world data, this approach falls short, very, very fast. And in this case, what happens when you have multiple vocals? Okay, this should be a video, but it's not playing. But anyway, when you have multiple vocals, forget about this idea of detecting the fundamental. It becomes a mess, and you can see it in this magnitude spectrogram here. There's like 4 or 5 voices, and that's where when things become really complicated. So at that point, we were like, okay, let's see if we can go the black box approach and see how far we can get. But what was important is that you don't need to swing between clear box and white box approach. There's some grace in between, and that's what this is mostly about, how to find the right balance and trade-offs between the two approaches. So inspired by, at the time, some of the advances in computer vision, we ask ourselves if this is possible, neural net, AI models that can learn to colorize images, that they can deblur images, that they can do super resolution, and you can think of these problems as kind of like reverse engineering problems. If this works, why could we not think about music, in this case, as an image, using one of these representations, in this case, the magnitude short time Fourier transform. So because this problem was originally pretty challenging to solve, we started with some baby steps and to try to validate some core principles, first principles that upon which we could extend to get to the final objective. So we started with, let's figure out if we can detect vocal activity in music. So we're talking about basically a binary classifier. And the way we designed this was, okay, we want to analyze with very small resolution whether there's vocal content in this segment that we're going to extract from the audio. So we want a good temporal resolution, but at the same time, because music is time series data, there's temporal dependencies, we need to provide some context around the prediction space to have the model be able to do this robustly. So what we ended up doing is designing a feature space that, given some context, would be able to tell whether the middle frame contain vocals or not. So these details are not that important, but this is what part of what feature engineering is about, and it's how you represent the data even before you put it through a machine learning algorithm so that it learns a certain task and derives into a model. And again, this started as a binary classification task, and very soon we realized, oh, this is a valid approach because we got like 97% accuracy on our test set. And back in the day, and this is 2015 basically, it was a lot of fun to start discovering, the effectiveness of these CNN networks, and it was really fascinating at the time to see how, trying to inspect and debug what was going on inside the models and how the model basically learned how to discriminate or came up with filters that knew how to extract vocal content or, filter out vocal content or filtering out music. So from there, we basically said, taking this binary classifier as a starting point, can we now go all the way to sort separation? So in a way, we're trying to go from a classification problem to a regression problem. And the original design was, okay, let's give this model a chunk of the music at the input, and let's see if it can fully recompose the magnitude spectrogram of the vocals only. So pretty soon we realized that that was too much to ask for that kind of model. Going back to the idea of constraints, these had to run in real time on a PC and share the GPU with some other rendering engines. So this was a highly constrained environment to try to solve this problem. You'll see that this model ended up having only 300,000 parameters, which is pretty low for given the complexity of the task. So we started getting creative. Okay, how can we try to frame the problem differently so that it seems like it's more simple than it really is, while still achieving the original objective. So we started playing with some heuristics and came up with an output feature space where we would oversimplify the task as this magnitude spectrogram representation as only allowing vocal or non-vocal content at each time frequency or each frequency bin, which is obviously far from reality, but at the end of the day, it kind of works. So we came up with this idea of these binary masks. And instead of asking the model to predict the full magnitude spectrogram, we asked the model to predict ones and zeros only. And with that, we could then apply this mask to the original representation of the magnitude spectrogram of the mix and somehow rescue the vocal from there. And that's kind of like what we did, and it worked really, really well. And eventually we moved from, instead of doing regression on this binary space, which doesn't make full sense, we started treating this as a multi-label classification problem, which was very cool, and it did the job. So this is an example of kind of like bringing the best of the clear box and the black box approach to come up with an efficient solution that works. And in this case, we effectively converted this regression problem into a classification problem. And this is the original design of the model. It's actually very, very simple, convolutional architecture. And don't worry too much about the details, because at the end I'm going to share some writings that I did on Medium a while back, and you have all the details about this work. Training data, which is always painful if you don't have an out-of-the-box training set. We spent months building this data set, conform of original mixes and the corresponding acapellas, and write a whole bunch of automation to automatically align them. And we ended up with a model that was trained on 15 million examples. And then we didn't stop there. Eventually, we said, okay, if this is working for vocals, chances are it might work for other instruments. And we built the first model to do source separation at the stems level, and it basically, in a single pass, could isolate vocals, drum space, and others. So we were not the first to do this, that there had been some prior art, but doing it in real time with such low number of parameters, yeah, it was a pretty big, significant contribution. And again, we're talking 2015, 2016. And we have some alternative designs for the stems model. Each of them had its pros and cons. And this is an example of that final model that could do stem deconstruction. Okay. I'm not sure why it's not playing the video now. Anyway, we're going to show, I'm going to share some of these things later. They're available as part of those articles. And in a nutshell, this ended up being a spin-off from that research at USC, with a vision to empower everyone to be part of and become an active part of the music creation process. It was called TuneSplit. Ended up having a small exit to another company, but it was a little ahead of its time. And today, 7-8 years later, you see these kinds of products. And Moses AI did something very similar. Back in the day, it was a little early, not only in terms of the readiness of the technology, but the readiness of the industry to embrace some of these ideas. But it's been very satisfying to see that these early ideas caught up, and now there's a lot going on in the space. And eventually, it's interesting how things went full circle, because eventually what we were trying to do is not just separate music just for the sake of it, but the idea that any person eventually could grab parts from different songs and recombine them, and making remixing accessible to anyone. And in a way, that's sort of what we ended up doing at Splice with COSO by Splice, which I'm going to cover in a minute. In terms of the value prop for the end user, ended up being something very in line with this. So yeah, it was a really interesting chapter with TuneSplit. And then fast forward a few years, I joined Splice in late 2017. So it's been 5 years and something. And it's been an incredible ride. And at this point, I need to switch to another document. So the Splice chapter, and very quick, what Splice is about. Splice empowers music creators everywhere, and today is kind of like leading player in offering the building blocks for music creation out there. And the kind of like the core offering of Splice, we have Splice Sounds, Splice Gear, and Creative Plans, and Splice Sounds is the marketplace of sounds, which has always been the flagship product, but there's a lot going on now in how we're going to evolve that value proposition with AI playing a key role in that. So when I joined, something that was very important is kind of like define a strategy for how we would go about applying AI to audio and music, or what would our music AI strategy be. And it was very important to keep in mind that we're successful when our customers realize the joy of making music. So keeping human decision making at the center was always critical, and that really not only affects in the way you design interfaces and UX, but it goes all the way back to how you build technology that's compatible with this goal, right? Very holistically, when I joined, the question was, does it make sense for a company like Splice to have, an applied research in AI operation? And the answer was yes. And what AI could do for a business like this was, on the one hand, accelerating the process of discovery, or the mechanics of discovery, And on the other hand, accelerating the creative process. What are those fundamental problems that creators face when trying to get started or making progress or finishing music? So these have been kind of like the core two areas in what the past 5 years have been about. So at the beginning, we started with a lot of classification problems. We really were focusing on how can we automate and scale our content library. And we did a whole bunch of things, and we started with a supervised approach, building some audio classifiers. These are some of the original designs. And they work pretty well. And what these classifiers enable, were on the one hand, is bringing consistency to the tagging. As we know, audio is a lot more subjective compared to images, so describing audio is inherently challenging. So having a model that could, even on a relatively reduced class space, predict what the content was about was pretty useful for that consistency. And also this complemented our ingestion pipeline and having kind of like a human-in-the-loop approach where the people who ingested content could rely on the model to try to accelerate the tagging process. And for this, we use pretty simple convolutional architectures with different approaches for performing multiple predictions and coming up with a final answer. And this worked pretty well. But eventually we realized that the supervised approach had many limitations, especially in the context of this massive catalog with lots of tags where not all of them could be learned by an ML model, or it didn't even make sense to automate that. So between that and also new opportunities that we could offer our users to discover the catalog in different ways, we started going the unsupervised route. And this led to our first user-facing feature, which was similar sounds. And in this case, we started training these autoencoder models that could come up with really high-quality embeddings of the audio data in our catalog and really dynamically capture pitch, harmonic profile, temporal structure, the semantics at times. And in a nutshell, what we did is design a system that given any sound from the Splice catalog, it could retrieve the most similar sounds at scale in milliseconds, and where the context or the concept of similarity is relative and it changes based on the inputs. So something very difficult to approach using a clear box approach or even a supervised learning approach. And this ended up working extremely well. It brought a lot of value to our users. It increased conversion. And this feature is currently available on the website, and I'll show you exactly how it works. So you can go to any sample in the Splice catalog. And I have this little button here that says show similar sounds, and it will just display the top 10 most similar sounds in the catalog. Let's check some other examples. Anyway, I love to use it with drum patterns, but it works with any sample from the catalog. It works with vocals, works with anything really. What was super interesting also, the core technology, we also deployed it internally to create a near duplicate content that makes it to the platform. And it also brought a lot of value during the pre-ingestion process. So even before a given sound makes it to the Splice marketplace, we run this internally to see if, for whatever reason, some of that content was a derivative of someone else's content. So it was an extremely valuable investment. Going back to the idea of accelerating discovery, accelerating creation, we also invested in a few experiments and projects on the acceleration of creative workflow, some generative AI back in the day, like this network that learned how to come up with new drum sounds. So none of these sounds exist. What you just heard were completely created by an AI model. It was inspired by the Style GAN 2 architecture and trained on a good number of drum sounds from the Splice catalog. Some of the other stuff we did around timbre transfer, basically taking any sound from the Splice catalog and trying to re-render it with a different target instrument.
I can show you what love is supposed to feel like.
Some other interesting stuff where you can bring the best of both worlds. In this case, we used this generative model that came up with new drum sounds, but instead of exposing that with the idea of, okay, now as a user I can create new sounds, using that to kind of like express what your intent is. Like, I designed this new sound, and part of the work that we did here was figuring out how to control the latent dimensions of this model so that you could say, okay, I want a drum sound of this BPM, this kind of density on the kicks and stuff like that. And we hooked that up with our similarity search technology to try to find the most similar human-made sounds available in the catalog, and it turned out to work really well. And this is an example of that. And anyway, and fast forward, what was like 3 years in, we started realizing that even though all these things were cool and some of them actually ended up in user-facing products that create a lot of value, the idea of investing in accelerating discovery and accelerating creation as two separate, disconnected states was not going to take us that far. So 2 years ago, we came up with a strategy that I called discovery-driven creation. Where the idea would be to develop not only technology, but a new way of thinking about the UX and interaction design between our users and the catalog, where now you could seamlessly jump between the states of discovery and creation. And that strategy gave birth to COSO by Splice, which is a new technology and a new product that we put out there, and a really valuable foundation on top of which we're develop on some really interesting stuff that's going to come out in the next few months. And without revealing too much, this technology that we created is not that different from similar sounds. We figured out how to project our audio data in some latent space, going back to the idea of latent spaces, where we can compare sounds, and the system can tell us, how well those sounds will fit together musically. And what's really interesting is that it can be parameterized at the same time. So given a reference sound, I can tell the system I need a funky acoustic guitar for a hip hop track, and in milliseconds at scale, the system will tell me this is the most compatible acoustic guitar that fulfills that criteria for that input sound. And not only that, the technology can search across tonalities, so you can find sounds that are not even on the same key. This does not implement any music theory rules or heuristic. This operates in a completely unsupervised at a layer below music theory, which makes it really, really powerful. So the Koso system can tell you this is the best, most compatible guitar, but you need to tune it down 2 semitones and stretch it by this percentage so that it matches the original reference BPM. And what we did, actually, the vision came for this product first, and then we went backwards and developed the technology. But eventually, we wanted to build this mobile surface that we describe as a inspiration engine, an idea starter, something that, given some intent, currently in the form of these templates, it comes up with original ideas that just sound really good. And more importantly, because it's very important to keep the user at the center and on the driver's seat, we developed this very simple mechanics to fine-tune these results. So when Koso gives you a starting point stack, a stack is the initial 8-byte arrangement that you see on the second plot, you can swipe right on any of the layers, and the system will bring you the next most compatible sample from the Splice catalog that fulfills the constraints of the style and all that. So it's been a pretty cool project, and yeah. So if you haven't downloaded it yet, here's the URL. It's pretty cool to play with. We don't need to go through that one. That's a promo video. And what's interesting is that we have our own philosophy and way to deploy AI technology and AI-based product. And in this case, we're combining a number of things. On the one hand, unsupervised content-based retrieval, which is also the case with the similarity search technology. But we're also bringing parametric search so that we can customize that content-based retrieval system. And the idea of multimodal intent, which is something that I'm personally very interested in, and I believe is the future of some of these AI-first products. And by that, I mean the different ways in which you can query a system. We see a lot of that currently, obviously, with the large language models using natural language as the mechanic to manifest intent. But intent can be in any form, especially with music. It could be a description of what I want, and we've seen that with the latest from Google, Music LM or Harmony. But it could also be in the form of a reference song that I heard on Spotify, and I'm like, oh, I want to create something in line with that in that neighborhood. So there's a lot to be explored around ways to capture intent. What's really cool about this technology is that is very extensible, and it can also work with MIDI. It's not limited to audio. So we did some cool experiments where now we're asking the system to give us good chords, chord progressions for a musical idea. So this is the guitar solo that many of you probably know. And Coaster in this case will create good arrangements to support that solo. And this is the top arrangement that the system came up with. Here, the second one. And it goes on and on forever. How about remixing a song? You know, here, why not combine some of the work on source separation and use the isolated vocals from a track as the seed for the COSO system? So here's the output of the source separation model. And once again, here I can give an instruction or a prompt, if you will, to the COSO system, asking for a song section that contains guitars, keys, and claps in the percussion. So you see that here, even though the system is not generative, like these days, it seems like everyone's talking about generative with reason. This is a different approach where we can almost emulate or replicate the same mechanics of these generative models, like providing a natural language interface. But in this case, rather than synthesizing the audio on the fly, what it's doing is matching human-made, super high-quality content in an intelligent way, so that no matter what you do, the arrangement will always sound musical. And that is an extremely good unlock and accelerator for creators. So when it comes to our approach to AI, at Splice specifically, and a big part of what I care about when it comes to AI, using AI to empower creation, in this case, rather than investing straight into generative stuff and all that, we try to unlock new layers of intelligence to serve human-made content more effectively. And the result of that first strategy gave birth to things like Similar Sounds, the first recommended for you system that Splice had, and COSO by Splice. And in addition to that, we can also invest in AI to extend the sonic boundaries of human-made content. And the stuff that I showed earlier about like timbre transfer, it falls under this category. And should we invest in fully generative stuff? Remains an open question. We've done some validations for that, but for now, it's really is our goal and mission to continue empowering creators through human-made content, and where AI can serve that content very well. And just to wrap up, what's next? There's for Splice, we are embarked on a mission to transform this amazing marketplace of sounds into a music inspiration engine. So in the next few months, you're gonna see lots of really cool things that are gonna be launched. And this is my personal assessment of what's next in general, not specific to Splice, but in terms of the kind of interfaces that we're gonna see that are powered by AI. The idea, again, of multimodal input, where rather than me having to adapt to the system adapts to me, and I can manifest what I want in multiple modalities. In natural interfaces, from 0 to 1 in seconds, the idea that I can, given an intent, I can get started with something that is good enough And more importantly, when trying to keep humans at the center of the decision-making process, fine-tuning mechanics. And that remains a pretty big challenge when building AI systems. There's different approaches like conditioning and all that, but that remains an open issue. Being able to be very granular in how you control an experience that's powered by AI is not an easy thing. And that's pretty much about it. And I had one last closing statement to kind of like philosophy for how to approach problems when it comes to so going back to kind of like the dilemma of clear box versus black box, and one versus the other, the answer is, in my experience at least, especially on the applied side of things, you don't want to make them compete. You want to bring the best of both worlds, and it's a trade-off. And trade-offs are at the heart of any successful product. And in this case, the trade-off is, if I go black box approach, I have less understanding and control. It's harder to fine tune and debug things. But at the same time, we can learn some incredible features that are beyond our understanding or ability to model. On the other side of the spectrum, I have more understanding and control. It's easier to control and fine tune and tweak my system, but we are limited to what we understand as humans. Or what we can model or make sense of. And with that, for those interested in getting more details about this design that around source separation, I published a couple of Medium articles with lots of details there. And this last one, what is the main reason most ML projects fail? So for any of you who are thinking or already working on applied ML to try to build products, highly recommend that one. Some lessons from the field, and that's all I have to say.
Fantastic presentation, Ale. I'll give it a couple minutes for anybody in the chat to ask any questions. One question that I had was, how big is your team? How big is the is your team that you work with?
Sure.
Or is it just you? Or is it just you that did all of this?
I could never make all this happen by myself. But we do have a pretty small team. I like to think that we have a very efficient R&D operation. Currently, we are 4 people as part of the core ML team. But when you see things like Coso the app or similar sounds, when it's time to build an actual product feature, then it becomes a broader team that's much larger, and a partnership between our team and the audio apps team and SRE and backend and front end. So, but yeah, the core team doing applied ML research is pretty small.
That's amazing. And how do you, when you find members for your team, what do you typically look for? Do you look for people that have already had experience in large data sets? How do you decide? How do you find somebody and say, this is somebody that's right for our team? I'm just curious.
I like the question because what I care the most is good decision making. People who are, and good decision making comes from mostly just common sense and being very pragmatic when solving problems. And especially in this area of ML and stuff, it's very easy to fall for guilty pleasure stuff. Oh, I want to do this because it's super interesting in school. So it takes being very intentional and very customer centric and product driven to make the right calls. So that's one first version of the answer. And just to support that, when you're doing applied research, you operate under really high levels of uncertainty. So it's very easy to get lost. It's very easy to end up on a rat wheel and start going around in circles. So really what I look for and what I think is the key to succeeding in applied ML is being very actionable and really making good decisions even when you don't know what the right call is, which sounds a little contradictory, but hopefully that makes sense. Obviously, people who have good domain expertise, but personally, I wouldn't trade unless there's something extremely specific that we need to unlock or accelerate. I care more about decision making and being able to navigate experimentation, which I believe is a whole discipline in itself, versus the specific skill set that you bring. Hopefully you bring both, but it's rare.
That's awesome. And this has been a discussion that I'm sure you've heard about, but with the amount of content that Splice has and the things that you're able to do, like you were saying, it sounds like at the center of the mission is making decision-making human-centric. How do you keep yourself from the temptation to say we don't even need producers to create drum kits anymore? We can just generate these ourselves and just.
Well, I mean, there's multiple answers. First of all, I'm also a creator. I'm also a musician, so I can definitely relate with what it means to be a creator. So I care a lot, and I definitely embrace the mission of empowering more creators. So that makes it easy. And the second one, it's part of my job. You know, for me to be successful and responsible in my role at Splice, I need to be very intentional around the strategies that I deploy. And for a company like Splice, that is the right approach. That's what we need to do to make Splice successful. Do I get tempted about trying more end-to-end stuff, you know, especially with the data set that we have? Sure. But and you know, to be clear, we do sometimes when time permits some internal R&D to be on top of all the stuff that's going on, even knowing that certain things will not end up on a user-facing product. But as I showed, you know, examples where you can bring the best of both worlds, right? So like the example that I showed where you have an end-to-end generative model, but instead of giving that generated drum kit back to the user, we use it as a way to manifest intent, to capture a query and surface human-made content. So you can get really creative with ways to also combine different AI models, but yeah, that would be my answer.
Nice. And do you have when you think 3 to 5 years down the line, in terms of what a creator looks like, what sort of tools that they'll be using, what sort of tools musicians will be using, what vision do you have?
Well, I guess the first answer to that is what I showed what I shared towards the end of the presentation. I consider it a new paradigm of interfaces. So it's not just about AI; it's a convergence of AI and just a new way to think about interfaces, where again you have multi-model input and natural interface, so with a very short learning curve, and the ability to get from 0 to 1 in seconds. Like when you think about, you know, music production, and just like many other things out there, it's not a mystery what makes a decent sounding track sound well. Like, you know, the rules of songcraft are widely known, the basics of maybe EQ mixing, and yet when you open a DAW, you start from scratch. So some of the interfaces are already obsolete in that sense, and we currently have technology that could solve some of those 0 to 1s. and fine-tuning mechanics. What are the ways, when you think about something like COSO, with a single swipe, you can change your arrangement, and it can be directional. That, I don't know if that answers the full question, but one way to answer it, products like COSO to me fall under that new category of creator interfaces. And obviously for us, that's not the end. We're going to be building more and more stuff. But zooming out for a second, I think we're moving into more web-based stuff that is collaborative by design. When you see things like Figma or Canva, that what they've done in the design world, I think we're all waiting and actively chasing what the equivalent or the music production version is going to be. And there's some players out there that are like giving it a shot. I was looking at the other day, I was watching what the guys from Never Before Heard Sounds are putting together, this kind of like Figma-like interface. So I'm not sure if that is the future, but it definitely validates some of these core principles that I can relate to. Mm-hmm. So yeah.
Yeah. Do you think that that the technology will move us away from the traditional DAW timeline-based grid system, or will that still remain in play just with some extensions to it?
Mm-hmm. I think that's a great question, and I don't think it's like, oh, is it going to be A or B? I think it's going to, the first question is, who are you building that for? I think that's the key. I think the DAW is going nowhere for certain type of creator and use cases. When you're trying to, create a ready Billboard Top 100 song, I mean, there's a lot of good complexity that can go in and a lot of granularity that you want and you need. So trying to replace the full extent and the full power of the DAW is a really long shot and a very risky one that I wouldn't sponsor. But I do believe that as powerful as the DAW is, it also presents lots of technical and psychological barriers for people who are not as comfortable, and especially people who are maybe beginners in music production, and especially for people who've never made music before. So I believe that's where the biggest opportunity is, interfaces that are more current, where you can get started in seconds with a very short learning curve. And I think for some people that might be enough, and there might be a new generation of services where some people don't ever get to the DAW because they have enough. And in the best case scenario, people who are somewhat confident with the DAW or proficient with the DAW, they're going to benefit also from AI technology in the form of either some sketching interfaces. Like in COSO is a good example of that. Like the COSO mobile app, you can, when you come up with something good, you can click a button and export that to an Ableton Live session and continue in the DAW. So that's an example of integrating things. And it could also come in the form of a VST plugin that's constantly aware about what you're doing in the DAW, and it really accelerates the process for you, surfacing relevant recommendations and so on. So I think it's going to be a bunch of things, and companies are going to have to be very aware and intentional around who are you building that for, because there's going to be no silver bullet of product that works for everyone.
Right. So it sounds like maybe the focus could be more towards more focused tools rather than a all-in-one solution like a DAW, from what you're saying, because there are going to be so many different workflows, and it could be about the integration of those different workflows rather than just an all-in-one solution.
Yeah, that's what I think. I mean, I wouldn't discourage anyone who's like, oh, I'm going to solve this. Chances are you're going to fail, but if you get it somewhat right, you could do very well. Right? But I don't know, maybe I change my mind eventually, but at this point, I think it's still a pretty long shot to think about one single next generation interface that's going to solve everything for everyone.
Absolutely. Looks like our listeners, watchers, viewers have run out of questions. A lot of positive feedback. Thank you very much, Ali, for sharing your insights. That was awesome.
My pleasure. Thanks for having me.